AS Quantum Physics 2, a bit more information about photons. So the energy of a photon, we've said E equals hf, where h equals Planck's constant, and as F equals c over lambda, we've got E equals hc over lambda. We're dealing with very, very small amounts of energy here. So there's a very useful unit of energy that we use a lot in physics, especially in the second year, and it's called the electron volt. And 1 electron volt is 1.6 times 10 to the minus 19 joules of energy. A very, very small amount of energy, 1 electron volt. Here's a little question for you to do. Calculate the energy of a photon of light from a red laser which has a wavelength of 660 nanometers. And I'll show you the answer in 3, 2, 1. And it is 3.2 times 10 to the minus 19 joules, or 2.08 electron volts. Here's another question that you should be able to do, a very typical A-level question. A photon of wavelength 220 nanometers falls on a zinc surface. The work function of zinc is 4.33 electron volts. Calculate the kinetic energy of the electron emitted in electron volts. And I shall show you the answer in 3, 2, 1. So we work out the energy of the photon in joules and then electron volts. And if we take away the work function from that, we get the kinetic energy of the electron, 1.32 electron volts. Here's another very common type of question. A small bulb has a power of 3 watts. Assuming that it is 10% efficient, how many visible photons does it emit every second? And we'll use the average wavelength of visible light, which is about 600 nanometers. I'll show you the answer in 3, 2, 1. 9 times 10 to the 17 photons. An obvious comment on that, that's a lot. There is an experiment. Well, there's several ways you can measure Planck's constant. I like this experiment. I think it's pretty straightforward and easy to understand. If we increase the voltage across a light emitting diode, inside the LED an electron jumps a small gap if it has enough energy, and when the electron jumps the gap it emits a photon, and the energy of the photon is EV, where V is the voltage needed to make the LED light up. And so what we do is we find out the minimum voltage needed to light LEDs, and we do it with LEDs of different colors. In other words, the photons have different wavelengths. And if we plot a graph of EV against frequency, then the gradient is Planck's constant. EV being the energy of the photon emitted, and then frequency, which we can work out from the wavelength. So HF against F, the gradient is going to be H. To get an accurate value for the minimum voltage, we need to know exactly the minimum voltage needed for it to light up. Your eyes should be adjusted to the dark. You look at the LED through a tube, you take several readings and take an average. Is there any other evidence that electromagnetic radiation comes in little packets? Well, consider gamma radiation. When gamma radiation is detected by a Geiger counter, you don't get a low hum, you get click, 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 click. The radiation arrives as packets of energy.